In statistics, linear regression is an approach for modeling the relationship between a scalar-dependent variable y and one or more explanatory variables denoted x. The case of one explanatory variable is called simple linear regression. For more than one explanatory variable, the process is called multiple linear regression. In linear regression, the relationships are modeled using linear predictor functions whose unknown model parameters are estimated from the data. Such models are called linear models. Most commonly, the conditional mean of y given the value of x is assumed to be an affine function of x. Less commonly, the median or some other quantile of the conditional distribution of y given x is expressed as a linear function of x. Like all forms of regression analysis, linear regression focuses on the conditional probability distribution of y given x, rather than on the joint probability distribution of y and x, which is the domain of multivariate analysis. Linear regression was the first type of regression analysis to be studied rigorously, and to be used extensively in practical applications. This is because models which depend linearly on their unknown parameters are easier to fit than models which are non-linearly related to their parameters, and because the statistical properties of the resulting estimators are easier to determine. Linear regression has many practical uses. Most applications fall into one of the following two broad categories. If the goal is prediction, or forecasting, or error reduction, linear regression can be used to fit a predictive model to an observed data set of y and x values. After developing such a model, if an additional value of x is then given without its accompanying value of y, the fitted model can be used to make a prediction of the value of y. Given a variable y and a number of variables x1, xp that may be related to y, linear regression analysis can be applied to quantify the strength of the relationship between y and the xj, to assess which xj may have no relationship with y at all, and to identify which subsets of the xj contain redundant information about y. Linear regression models are often fitted using the least squares approach, but they may also be fitted in other ways, such as by minimizing the lack of fit in some other norm, or by minimizing a penalized version of the least squares loss function as in ridge regression and lasso. Conversely, the least squares approach can be used to fit models that are not linear models. Thus, although the terms least squares and linear model are closely linked, they are not synonymous. Introduction to linear regression. Given a dataset of n statistical units, a linear regression model assumes that the relationship between the dependent variable y and the p-vector of regresses xi is linear. This relationship is modeled through a disturbance term or error variable epsilon I, an unobserved random variable that adds noise to the linear relationship between the dependent variable and regresses. Thus, the model takes the form where t denotes the transposed, so that xit beta is the inner product between vectors xi and beta. Often these n equations are stacked together and written in vector form, as where some remarks on terminology and general use is called the regress and endogenous variable, response variable, measured variable, criterion variable, or dependent variable. The decision as to which variable in a dataset is modeled as the dependent variable and which are modeled as the independent variables may be based on a presumption that the value of one of the variables is caused by, or directly influenced by the other variables. Alternatively, there may be an operational reason to model one of the variables in terms of the others, in which case there need be no presumption of causality. Are called regresses, exogenous variables, explanatory variables, covariates, input variables, predictor variables, or independent variables. The matrix is sometimes called the design matrix. Usually a constant is included as one of the regresses. For example, we can take xi1 equals 1 for I equals 1. The corresponding element of beta is called the intercept. Many statistical inference procedures for linear models require an intercept to be present. so it is often included even if theoretical considerations suggest that its value should be 0. Sometimes one of the regresses can be a nonlinear function of another regressor or of the data, as in polynomial regression and segmented regression. The model remains linear as long as it is linear in the parameter vector beta. The regresses Xij may be viewed either as random variables, which we simply observe, or they can be considered as predetermined fixed values which we can choose. Both interpretations may be appropriate in different cases, and they generally lead to the same estimation procedures. However, different approaches to asymptotic analysis are used in these two situations. Is a p-dimensional parameter vector. Its elements are also called effects, or regression coefficients. Statistical estimation and inference in linear regression focuses on beta. The elements of this parameter vector are interpreted as the partial derivatives of the dependent variable with respect to the various independent variables. Is called the error term, disturbance term, or noise. This variable captures all other factors which influence the dependent variable y other than the regresses xi. The relationship between the error term and the regresses, for example whether they are correlated, is a crucial step in formulating a linear regression model, as it will determine the method to use for estimation. Example: consider a situation where a small ball is being tossed up in the air and then we measure its heights of ascent high at various moments in time t. Physics tells us that, ignoring the drag, the relationship can be modeled as where beta 1 determines the initial velocity of the ball, beta 2 is proportional to the standard gravity, and epsilon I is due to measurement errors. Linear regression can be used to estimate the values of beta 1 and beta 2 from the measured data. This model is nonlinear in the time variable, but it is linear in the parameters beta 1 and beta 2. If we take regresses xi equals, the model takes on the standard form assumptions. Standard linear regression models with standard estimation techniques make a number of assumptions about the predictor variables, the response variables and their relationship. Numerous extensions have been developed that allow each of these assumptions to be relaxed, and in some cases eliminated entirely. Some methods are general enough that they can relax multiple assumptions at once, and in other cases this can be achieved by combining different extensions. Generally, these extensions make the estimation procedure more complex and time-consuming, and may also require more data in order to produce an equally precise model. The following are the major assumptions made by standard linear regression models with standard estimation techniques. Weak exogeneity. This essentially means that the predictor variables x can be treated as fixed values, rather than random variables. This means, for example, that the predictor variables are assumed to be error-free, that is, not contaminated with measurement errors. Although this assumption is not realistic in many settings, dropping it leads to significantly more difficult errors in variables models. Linearity. This means that the mean of the response variable is a linear combination of the parameters and the predictor variables. Note that this assumption is much less restrictive than it may at first seem. Because the predictor variables are treated as fixed values, linearity is really only a restriction on the parameters. The predictor variables themselves can be arbitrarily transformed, and in fact multiple copies of the same underlying predictor variable can be added, each one transformed differently. This trick is used, for example, in polynomial regression, which uses linear regression to fit the response variable as an arbitrary polynomial function of a predictor variable. This makes linear regression an extremely powerful inference method. In fact, models such as polynomial regression are often too powerful, in that they tend to overfit the data. As a result, some kind of regularization must typically be used to prevent unreasonable solutions coming out of the estimation process. Common examples are ridge regression and lasso regression. Bayesian linear regression can also be used, which by its nature is more or less immune to the problem of overfitting. Constant variance. This means that different response variables have the same variance in their errors, regardless of the values of the predictor variables. In practice, this assumption is invalid if the response variables can vary over a wide scale. In order to determine for heterogeneous error variance, or when a pattern of residuals violates model assumptions of homoscedasticity, it is prudent to look for a fanning effect between residual error and predicted values. This is to say, there will be a systematic change in the absolute or squared residuals when plotted against the predicting outcome. Error will not be evenly distributed across the regression line. Heteroscedasticity will result in the averaging over of distinguishable variances around the points to get a single variance that is inaccurately representing all the variances of the line. In effect, residuals appear clustered and spread apart on their predicted plots for larger and smaller values for points along the linear regression line, and the mean squared error for the model will be wrong. Typically, for example, a response variable whose mean is large will have a greater variance than one whose mean is small. For example, a given person whose income is predicted to be $100,000 may easily have an actual income of $80,000 or $120,000, while another person with a predicted income of $10,000 is unlikely to have the same $20,000 standard deviation, which would imply their actual income would vary anywhere between $10,000 and $30,000. Simple linear regression estimation methods give less precise parameter estimates and misleading inferential quantities such as standard errors when substantial heteroscedasticity is present. However, various estimation techniques can handle heteroscedasticity in a quite general way. Bayesian linear regression techniques can also be used when the variance is assumed to be a function of the mean. It is also possible in some cases to fix the problem by applying a transformation to the response variable, independence of errors. This assumes that the errors of the response variables are uncorrelated with each other. Some methods are capable of handling correlated errors, although they typically require significantly more data unless some sort of regularization is used to bias the model towards assuming uncorrelated errors. Bayesian linear regression is a general way of handling this issue. Lack of multicollinearity in the predictors. For standard least squares estimation methods, the design matrix X must have full column rank P, otherwise, we have a condition known as multicollinearity in the predictor variables. This can be triggered by having two or more perfectly correlated predictor variables. It can also happen if there is too little data available compared to the number of parameters to be estimated. In the case of multicollinearity, the parameter vector beta will be non-identifiable. It has no unique solution. At most we will be able to identify some of the parameters, i.e., narrow down its value to some linear subspace of Rp. See partial least squares regression. Methods for fitting linear models with multicollinearity have been developed. Some require additional assumptions such as effect sparsity, that a large fraction of the effects are exactly zero. Note that the more computationally expensive iterated algorithms for parameter estimation, such as those used in generalized linear models, do not suffer from this problem, and in fact it's quite normal to, when handling categorically valued predictors, to introduce a separate indicator variable predictor for each possible category, which inevitably introduces multicollinearity. Beyond these assumptions, several other statistical properties of the data strongly influence the performance of different estimation methods. The statistical relationship between the error terms and the regresses plays an important role in determining whether an estimation procedure has desirable sampling properties such as being unbiased and consistent. The arrangement, or probability distribution of the predictor variables X has a major influence on the precision of estimates of beta. Sampling and design of experiments are highly developed subfields of statistics that provide guidance for collecting data in such a way to achieve a precise estimate of beta interpretation. A fitted linear regression model can be used to identify the relationship between a single predictor variable xj and the response variable y when all the other predictor variables in the model are held fixed. Specifically, the interpretation of beta j is the expected change in y for a one-unit change in xj when the other covariates are held fixed, that is, the expected value of the partial derivative of y with respect to xj. This is sometimes called the unique effect of xj on y. In contrast, the marginal effect of xj on y can be assessed using a correlation coefficient or simple linear regression model relating xj to y. This effect is the total derivative of y with respect to xj. Care must be taken when interpreting regression results, as some of the regresses may not allow for marginal changes, while others cannot be held fixed. It is possible that the unique effect can be nearly zero even when the marginal effect is large. This may imply that some other covariate captures all the information in xj, so that once that variable is in the model, there is no contribution of xj to the variation in y. Conversely, the unique effect of xj can be large while its marginal effect is nearly zero. This would happen if the other covariates explained a great deal of the variation of y, but they mainly explain variation in a way that is complementary to what is captured by xj. In this case, including the other variables in the model reduces the part of the variability of y that is unrelated to xj, thereby strengthening the apparent relationship with xj. The meaning of the expression, held fixed, may depend on how the values of the predictor variables arise. If the experimenter directly sets the values of the predictor variables according to a study design, the comparisons of interest may literally correspond to comparisons among units whose predictor variables have been held fixed by the experimenter. Alternatively, the expression held fixed can refer to a selection that takes place in the context of data analysis. In this case, we hold a variable fixed by restricting our attention to the subsets of the data that happen to have a common value for the given predictor variable. This is the only interpretation of held fixed that can be used in an observational study. The notion of a unique effect is appealing when studying a complex system where multiple interrelated components influence the response variable. In some cases, it can literally be interpreted as the causal effect of an intervention that is linked to the value of a predictor variable. However, it has been argued that in many cases multiple regression analysis fails to clarify the relationships between the predictor variables and the response variable when the predictors are correlated with each other and are not assigned following a study design. A commonality analysis may be helpful in disentangling the shared and unique impacts of correlated independent variables.